Hello, am I audible now? Hello?
Yes, ma'am. Yeah.
Okay, yeah. Good. So, did you guys try to figure this 2.2?
Yes, ma'am.
And what did you do? What was your very first step?
Drew the diagram.
The transition diagram, right?
Yeah.
Okay, so let me just draw the transition diagram. Let us say, they haven't given us the name of the states. So let us define them by ourselves. So this is state 1, 2, 3, and 4. So I can just draw state 1, state 2, state 3, and state 4. Okay, so there is nothing from 1 to 1. From 1 to 2, it says 1. Okay. Let me just be precise. And then nothing. So 2 to 3 is 1. Okay, I'm very much used to drawing arrows. Then it says 3 to 4 is 1. And from 4 to 1, okay, there's something where you can move from 4 to 1. And that is 0.5. And then you have 4 to 3 back, which is 0.5 again. Yeah. And then what did you do?
So then it is irreducible, right? Because I can go from any point to any other point.
It is not
Exactly.
irreducible, no?
And why do you think it is not irreducible?
Because you can't go from 2 to 4, right?
Okay, let's see. I can go from 2 to 3 and then I can move from 3 to 4. So whenever
Okay, directly. Okay, sorry.
Yeah, perfect. So it doesn't mean that we should be able to go over there directly. So I guess that's cool. Okay. Yeah. So is this irreducible? Let's see. So from 1 I can go to 2. Yes. From 1 I can go to 3 via 2. And I can go to 4 via 3. And from 2 I can move to 1. Can I? 2 to 3, 3 to 4, and then 4 to 1. Yes. I can go from 2 to 3. I can go from 2 to 4 as well. 3 to 1, 3 to 4, and then 4 to 1, right?
So actually, if you interchange the 3 and 4 positions, it becomes much easier to understand. So it forms like a perfect circle with only like interchange between the 3 and 4.
Yeah. I guess that's fine. So yeah, I think even if you do that, I guess that will just make it a bit easier to see if it's irreducible or not. And once you do that, then what's left? Okay, I think I shouldn't have erased that. So I will just do this. So 1 to 2 was 1, 2 to 3 was 1, 4 to 1 was 0.5, 4 to 3 is 0.5, and I guess 3 to 4 is 1. Okay, yeah, yes, this is much better. So what do we have? Now if we have irreducible, so we have concluded that this Markov chain is in fact irreducible. Okay. But what we are asked is to figure out the periods of each of the states in this chain. So what do you think I can do
all of
next?
the periods, like the period of 1, 2, 3, and 4 will be the same because it's irreducible.
Exactly right. And that is something that we have already seen in the lecture. So I'm not going to repeat all of that again here. So I know that the periods of each of these states is going to be the same. So let us try to derive period of any one of these states, and who will help me with that?
I'll do it.
Okay, let's do it for 1.
So to reach 1, right? In one step, you can reach from 4.
Can you do that?
Yeah.
So I'm starting, okay, no. So whenever you figure out the period, you start in state 1, and now you want to check how you can reach state 1 again.
Okay, so 1 to 2. 2
yeah,
to 3.
That is 1, 2.
Then 4. Then again back.
Right. Yeah. So how many time steps did we cover? So this was 1 step, 2 step, 3 step, and then 4 step, right? So I'll write 4. Is there any other possible path that I can take to reach 1?
Yes, so we can go from 1 to 2, 2 to 3, 3 to 4, back to 3 again, and then back to 4, and then to 1. So that will be 6 time steps.
So that will be 6 time steps, right? Because we're adding up 2 more time steps where I go back to 3 and then come back to 4. So these 2 can happen as many times as I want. So in this case, we never looped back. But in this case, we looped back once. And if I looped back again, let's say 2 more times, let's say 2 times, then I'll have 6 plus 2, 8, and so on and so forth. So the highest common factor for all of these is 2. Right? I can divide all of these by 2 and I will get some integer value. So the period of state 1 is 2. And so will be the case for each other states as well. Because we have concluded that this Markov chain is irreducible in nature. Any doubts? Anyone?
No, if we have to check for 3 now, or we check only for 1?
Let us do that. So let's check it for 3 and we'll see what happens. Okay. So if we check for 3, let's say we check for 3. So Sahil, I want you to do this. What should I write first? How can you come back to 3?
So 3 to 4 and 4 to 3.
How many time steps?
2 steps.
Okay. Next.
Okay. Then 3 to 4. Then like
the whole
3
circle.
to 4 and 1 to the whole circle. Okay,
exactly right. So 1, 2, 3, and 4. So you'll have 4, and then you will be adding up basically. So there is nothing else, I guess, because you will eventually. So again, the common factor is 2. So if you do the same for each of these as well, you will get 2 as the answer. And again, because we have this fact already established that if a Markov chain is irreducible, then the periods of all the states in that Markov chain are same. Is same.
Understood.
So that is why it's going to be 2 anyways. So you don't have to do that calculation. So any doubts, anyone? Any doubts? Okay. So let me move to the next question. Let's do question 2.4. Okay. So this question, who would want to volunteer into reading this question? Anyone?
I'll do it.
Okay, go on. Thank you.
I have to read it, right?
What do you say?
I have to read the question now?
Yes.
So basically, a new actual student is planning to sit one exam each session. He expects that his performance in any exam will only be dependent on whether he passed or failed the last exam he sat. If he passes the given exam, the probability of passing the next will be alpha, regardless of the nature of the exam. If he fails an exam, the probability of passing the next will be beta.
Yeah, that's it. Thank you very much, Sahil. Okay, so now what information do you get in each of the sentences in this question? Let us try to decode that, okay? What information can someone, if you guys can see, is there in the very first statement? Is there any information that we can use in terms of math? So we only know that there is one exam per session, right? There is no more than one exam that the student is sitting in a particular session. So we keep that in mind. And then we have something else here. So they're saying that the performance in today's exam will depend only on the last exam, not any exam that this particular student has taken prior to previous exam. So this is what property?
Conditional property.
What property did you say?
Conditional probability, right?
Yes, so it is conditional. Yeah, it is conditional. What else?
Markov
as well, right? So it is conditional, but it is also Markov because only the last information matters. Nothing previous to that will change what's going to happen in the future. Okay. And next, what do we have? If he passes a given exam, so can you guys guess what are the states? So let's say if you were to denote this particular process using a Markov chain, what kind of a process will you use? So what kind of states will you have? Anyone?
Exam, pass and fail.
What did you say?
1, 2, 3, 4, right? No.
And why do you think it will be 1, 2, 3 for Sahil?
Because he's saying now, like, probability of passing the next will be beta if he passes this exam. So I'm not sure about this.
I think it would be exam, pass and fail.
Exam pass and exam fail. Okay. So Sahil says 1, 2, 3, 4. And Sahil, you are yet to say what these 1, 2, 3, 4 are. Vanshisa says it should be just pass and fail. Okay.
No,
What
three
else?
states. Attempting, like appearing exam, pass and fail.
And what exactly are you trying to say there, Vanshita? Can you elaborate? I mean, this is the result of the exam, right? Pass and fail.
Yes, but then, okay, just I think it will be the exams itself. So if we are considering that he's giving n exams, then it will be that way. So 0 to n.
0 to n. Okay. So the number of exams.
Yeah.
Okay. Here we are considering the result of exam. Okay.
My thought was like it would be appearing in exam, then like the probability that there are two ways. So either it will be like the student will be passed or fail with probability
Yeah.
beta respectively, and then like if failed, it again connects to exam appearing the exam. That's what I thought. I don't know if it's right or wrong, but.
Okay. So, okay. What did you say, Savri?
I think it will be 4. The first state will be the student appears, like he fails and then passes. Second will be passes, then again he passes. And the other two will be he fails the first. Sorry, just a second. I'll just fail. Yeah, fail, pass, 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 fail, fail, and pass, fail.
Okay. Okay. So now when you transit from these states, let's say I'm defining these 4 states, 1, 2, 3, 4. Okay. So what do you think will be the probability that I go from 1 to 2? What is this saying in terms of words? Can you tell me that, Sauri? So when I say that I'm moving from state 1 to state 2, I'm saying that I failed the exam and then I passed another exam, and now I have passed 2 exams.
Yeah, this is right now.
It will be alpha, right?
It will be alpha.
Okay. You think it should be alpha? Okay. What is alpha? Let's see. If he passes a given exam, the probability of passing the next will be alpha, right?
Yeah.
But here what you have done is, I mean, again, I can say that this to this should be alpha. Is there any difference? Is there any difference when I'm moving from 1 to 2 and 2 to 4?
But how can you move from 2 to 4?
Why can't I move from 2 to 4?
Because like third exam is skipping. Like is it that way?
I don't know. I mean, did you guys? Okay. So wait. So do you think they should be PF and they should be FF? I guess that is what you guys must have meant. so that I transit to 3 directly. So this should be PF and this should be
Yeah, this will
FF.
be FF.
Okay, and you think this should be alpha. Okay. Okay. So tell me one thing. If I am at one particular state, right, and I move to another state, what should matter? If I were to characterize this as a Markov chain, I know that the Markov property should also be satisfied, right?
Yes, ma'am.
And what does my Markov property say?
Depends on the current state.
Yeah. If we are in the current state, then
So if he has to go from 3 to 4,
yeah.
then it should be 1 minus beta, right?
Okay, from 3 to 4, you say it should be 1 minus beta. See, but again, this is just some chain, right, that you are creating now. Is this a Markov chain? That is my question. So we want to check whether this chain is a Markov chain or not. So I guess this is what Isha was trying to say. So I'm going to erase this and we'll see this case later on maybe. So what does my Markov property say? Anyone?
That the next probability should depend only on the current state.
Okay, that's correct. But I want it in terms of this example. This precise.
I think for the third state, if you are telling that from state 2 to 3, you are in the past state, means at the third you are passing the exam. And on the third state, how can you also fail the exam and then go to fourth state?
Exactly right. So, okay.
Ma'am, I think that the way we've done the 25 minus and 25 plus, like 25% minus and plus situation, it will be something like that. So it's like if you pass an exam. So I think here the thing is about how we proceed from the first exam. So like how do we start with that, because we don't know anything about the past, right? So how can we consider that? Like you said, for 1 to 2, like alpha is only if we know that he's already passed an exam, right? So what do we take the first probability as?
Okay, so that is I mean, this clearly says that Markov property is not getting satisfied here, because if let's say, if I were to say that this chain should be a Markov chain, and I would know that to see what is my chance of going from 1 to 2 should only depend on the fact that I am at 1. It shouldn't matter how or from where I have arrived at 1, right? The very fact that my probability of passing another exam should only be dependent on my current state, right? Which is I have passed one exam. But is that the case? No. Here it really matters whether I have come to 1 by passing another exam, or was I still at 1 and I failed one exam, so I'm still at 1. So this 1, 2, 3, 4 will be, let's say if I define n, this will be the number of exams passed, right? According to you guys. So if I try to model the number of exams passed, I see that this chain is not clearly Markov, right? So what else can we do now? So sometimes it isn't only the question about representing the thing that you think is state space, because what also might happen is, let's say now we are saying that my n, which is the number of exams passed, I'm thinking that as my state space. But let's say if we do some reverse engineering. And what I do is, I only read this question. Okay, so if he passes a given exam, the probability of passing the next will be alpha. Okay, so let's say if I go with what Vanshita said, let us say I write here P, then I know that the probability of passing the next will be alpha. So if I am at P today, the chance that I will find myself again at P is alpha, right? Regardless of the nature of the exam. Forget about it. If he fails an exam, the probability of passing the next will be beta. So let us say if I write F here, the probability that I will pass the next exam is going to be what? Beta. But again, what is this P and F? This P represents that I have passed my previous exam. And this F represents that I have failed my previous exam. So we have made those two as our states. And now I say that if I have passed my previous exam, the probability that I will pass my next exam is also alpha. So again, remember, you have to be able to denote, you should be able to denote these transition rates and these states. So again, this will come with a bit of a practice, and you will have to start thinking not only mechanically, but also intuitively of, let's say, if you were supposed to write a transition matrix here, how would this look like? So if you have 1, 2, 3, 4, is this a Markov? This is for sure a chain, but is this a Markov chain? Because that is what I want. And again, the very easiest way to solve these kind of questions and to figure out what your states should be is to figure out what these probabilities are precisely for. So here you see that alpha is the probability that if I have passed one exam, I will pass my next exam as well. So you can think in your mind that this is just passing one exam and then passing another exam. So P to P, and that is just alpha. And then the next statement will give you this F to P. So now if I give you guys this information, what do you guys think should I write on these two different arrows? So what will be F to F? What is the probability that if I have failed my last exam, I will fail the next exam?
1 minus
1 minus beta.
Precisely, yes. And this will just be 1 minus alpha, right? So this will be your transition matrix now. So if you were to write your transition matrix, this, so let's say PF, so P to P alpha, 1 minus alpha, beta, 1 minus beta, and this will be beta, right? And I guess what we did now is the second part of the question. Okay, so now that we have derived this, okay, so for the guys who thought this would be, this could be the possible state space, do you guys understand why is this not a state space? And why, if we have this is not a Markov chain? Okay, good. What about Sahil?
Yeah, ma'am. I just wanted to, can you
Just call me
explain once
Kashmira.
again? Sorry,
Yeah.
can you just explain once again that why did we choose this instead of that?
Okay,
1, 2, 3, 4.
so
Like,
yeah, so
where was I wrong in this? I just wanted to understand.
let me just explain to you. So when I say that these are my states, right? So I'm saying that this one here represents that I have passed one exam up until now, right? And there are two different ways you can arrive at this one, right? Let us say you have passed the previous exam and you started off your journey, you passed one exam, and that is why you are here at 1 today. Okay, so you have one exam passed, or else you took the exam last year and you failed, and that is why you are taking again the exam. So you would still be at 1, right? If you pass that exam. So again, there are basically, so let us say, okay, I think I said the last sentence bit wrong. So there are two different possibilities. One is the case where you didn't take any exam and you pass the exam, so you have one exam cleared. Or else you tried to take one exam and you failed, and then you again tried to take the exam and you failed.
Okay.
So that would, so basically the very fact that you are at 1 is possible
Only
in
if I
two
fail
different
first.
ways. Yeah. So, okay, no, wait. Let me just, I don't remember what I said, but forget all that. Let me just say it in different words. The very fact that you will go from 1 to 2. So the probability that you will pass another exam and you will move from 1 to 2 is dependent on how you arrive at 1. Whether the previous exam you passed was, whether the previous exam you took, you passed or failed. So if you passed that exam, then there is a probability alpha that you will pass another exam. But if you failed the exam, then you know that this is not alpha, this would be beta, right? So that is why you cannot say for sure what this probability will be until you know from where you're coming. So again, here you will have a self transition loop, right? 1 to 1.
Yeah.
So you have one paper cleared.
Okay.
Yeah, so you have one paper cleared already and you tried to take another paper and you failed that. So at present, you do have only one number of paper passed.
Understood.
So yeah, it matters if you arrive at 1 from this loop or from this loop to go from 1 to 2.
Understood.
Okay, perfect. All right. So now can you guys try to solve this part 1A? So I'm just gonna erase this part. Should probably use eraser. I'm gonna use this as well. And everything else as well like this. We'll keep this. Ideally we solved the second part first. So you shouldn't be requiring this to solve these.
So will it be something like for the first A part, will it be something like alpha raised to 6 into 1 minus alpha?
Okay, you say alpha raised to 6 into 1 minus alpha. Okay, so what is the question trying to ask us? We want to figure out the probability that the first exam he fails is the 7th exam, given that he passes the first exam. So we are given that the very first exam that this guy took, he passed it. Okay, so let us.
Will it be alpha raised to 5?
And why do you think it should be alpha raised to 5?
Because first exam he has passed. Okay, so you'll start from the second exam. Okay, the second, 2, 3, 4, 5, 6, right?
Okay, yeah.
And seventh exam he has failed.
Yeah, that is indeed correct. So let me just try to write that nicely. Okay, so if I have this, I know I'm being given that he has passed the first exam. So I do not take this into consideration now. All I care about is what happens from 1. So if you look at the number of transitions that you will be making, it is 1, 2, 3, 4, 5, and 6, right? So out of these, so to reach the 7th exam, you have to only make 6 number of transitions. And that is the sum that you should get in the power over here. So you know that he has failed the 7th exam. And the first exam he fails is 7th. So we know for sure that he has passed all of this. So probability that he has passed this, that he will pass the next exam is alpha, 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 alpha. And
so
the next
we are
exam,
starting from the point of the first exam, like after the first exam is over. We are not starting from the beginning.
Yeah, right. Because they've given to us that that this guy has passed the first exam. So the first exam is passed, and that is what we know. And that is how we know that we are in this particular state. And now we are given that he passes all the exams because the first exam he fails is the 7th exam that he takes. So again, remember, this is the exams, not the number of exams he has passed. So this will just be alpha, 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 and this will be 1 minus alpha because we want him to fail the 7th exam, right? So if you do that, you get alpha raised to 5 times 1 minus alpha, and that will be the chance of observing A. Does this make sense? Any doubts? Okay. So now we'll try to do the B part. Yeah. He passes the 5th exam, given that he fails the first 3. So we know that he has failed the first 3, and we only care about up until 5.
There'll be 2 parts.
So I know that when I'm at 3, there will be?
There'll be like 2 parts in this, now. Like either 4th exam he'll pass or fail. So if he passes
Exactly.
the 4th exam, that means he went from fail to pass. So basically that'll be beta.
Yeah. Yeah.
And then for 5th exam he has passed, fail.
Yeah.
So
he passes the 5th exam.
Which will be alpha.
Which will be alpha. Yes.
Plus.
Okay, wait. Let me just
he has
write
failed the exam.
Yeah, exactly. This won't be
yes.
alpha. This will be, wait, let me just write what we just did. We said that he failed the first exam. So given that we know that he has failed, so we said he failed the 4th exam, and then he has to pass the 5th exam, right? So F to P is beta, and F to F is 1 minus beta. So this path will not have this probability. This path will have 1 minus beta times beta, right? 1 minus beta for F to F, and then for F to P, you have beta. Do you get that, Sahil?
No, but this is the only answer. But what if he passes the 4th exam?
Exactly, right? So that you will add now. So you add to this another possibility, F to P, and then P to P. So now, because this is only one sample path, but again, you can pass the 5th exam that you take, given that you have already passed the 4th. So F to P, what's the chance? From F to P, you will have beta. And then from P to P, you will have alpha. Right? So these are 2 possible sample paths that you can have. And that will be the precise answer for your B part.
Ma'am, I think it would be beta into alpha square because like till 3 we know that he has failed the first 3, right?
Yeah, so we know that the last exam he took, he has failed that. And this is what I have written F for.
Okay, so after that, so while he's moving from 3 to 4, will it be beta?
Why do you think it will be beta? So again, I mean, it could be 1 minus beta or beta, right? Depending on whether you assume he's passing the 4th exam or he is failing the 4th exam. So if he fails, it's 1 minus beta. And if he passes, that's going to be beta. Right?
So right now, do we have to only consider what happens to from 4th to 5th and then 5th and ahead, like the 5th one exactly?
No, not quite that. Okay, so we forget about states. Think of it in terms of transitions, right? States, I mean, states are P and F. And what the number of exams that you do are 3, 4, and 5. Okay, these are not the number of exams that you have passed. These are in total the number of exams you have taken. Okay, and they're saying that he has failed the first 3 exams. So 1, 2, 3, which I haven't written. So he has failed the first 3 exams. All right. So the 3rd exam that he took, he failed that exam. He failed that exam. Right. Now I have to see what is the chance that he will pass the 5th exam? So if this is 3rd exam, this is the result of 4th exam, and this is the result of 5th exam. And so is this the case. But I know that he has passed the 5th exam, and that is the probability that I care about. So I do this, and I write P here. And now what I have to see is all the possible values that this 4th exam can take. Right? So I could either fail or I could pass. So I have F and I have P respectively. But again, the number of terms that you will have, the number of probabilities that you will have is the number of transitions that you make. And the number of transitions that you make is always one less. So if you have F, F and P, you only make one transition from third to fourth, and then from fourth to fifth, you make another transition. So you have failed the first 3 exam. But again, to go from 3 to 4 is one transition. And then to go from 4 to 5 is the second transition. Does this make sense?
And so it's like from fail to fail and then from fail to pass. Or yeah, so fail to pass and then pass. So 1 minus B into the next stage.
Exactly. So this 1 minus B corresponds to the probability. Given that I have failed the last exam, I will fail my today's exam. And this beta is F to P. And this beta here is again F to P, and this alpha is P to F, sorry, P to P.
Got it.
All right. Okay. Any more doubts with this? Anyone? Mihir, any doubts?
No, ma'am, it's clear.
Okay, perfect. I guess you would have had the same doubt about the powers. Was that your doubt?
I was able to solve the first part, means A part, but I was not able to draw the transition diagram. So it was.
Okay. All right. No worries. So I guess this is clear now. Good. So let us move to solving another question, which is this 2.6. I guess we should do this ideally because I kind of messed up while I was explaining in the lecture about about stationary distributions. So I think I owe you guys at least one question solved for this stationary distribution. So, okay. Can anyone recall the property of stationary distribution? So let's say if I were to figure out the stationary distribution for this, and let me just, for convenience, 1, 2, 3, 4, 5. Okay, we aren't going to solve this much. I'm not going to solve for all the equations, but I just want to give you guys the idea of how to write those equations in the first place.
And we have to also solve the revision notes, right?
Yeah.
Oh.
So that revision notes is the past paper questions from the respective chapters.
Okay.
Yeah. So once I think the very first thing that you should do is after you understand the concepts well from the chapter, go through the end of the chapter questions, and once you make sure that you have understood thoroughly all the so again, when you try to do this end of the chapter questions, never try to look at the answer first. Try to solve it using the concepts, and then you will get to know where the loophole is in your understanding. So that's one way to know where you need to work. And then you would go to revision notes ideally once you have known and understood all the concepts well. Because over there, it's not that in one question you'll be using only one concept. There you will be using 2 or 3 concepts in, let's say, one question. So
I still have a doubt in incremental parts. Like when you do incremental, like what kind of questions will come in incremental? Like y n plus 1, something goes there. Hello?
wait, yeah, I'm here. You mean something like this?
Yeah, I always face doubts in this. Right.
Okay. Do we want to solve this question? I guess we can solve this question. So let us do 2.6.
We'll like C part we'll solve it on our own. It's just that the first two parts can you solve it like this together basically.
Yeah. Okay, fine. Let's just solve this first, I guess. I mean, stationary distribution is really not that difficult. So let me just start off with this. Okay, but I want each one of you to read the question first. And we'll try to go step by step. Okay, so we have a stochastic process xt, and we are defining a relationship that xt is just equal to zt plus zt minus 1. And they have given the probability distribution of zt here. So it can either take a value of 1 or a value of 1000, and 1 with the probability p and 1000 with the probability q. And you know these are mutually exclusive and exhaustive, so of course p plus q is 1. Okay, and they've also given this information that q is less than p. So there's a greater chance that you will observe your value of zt as 1. All right, so now we have to figure out what is the probability that your x5 will be 1001. Okay, this is actually a good question. Thank you very much for asking this, Sahil. Okay, so what do you guys think I should do here?
XT will be Z5 minus Z5 plus Z4, right? Like X5 is equal to Z5 plus Z4, right?
Of course. So if I were to write this probability, I can write this X5 using this expression as Z5 plus Z4. So I can write here Z5 plus Z4 being equal to 1001. Okay. And what else can I do? So Sahil, I do not want you to speak. I guess you already know this. So what do others think about this? What should I be doing next?
And to get to 1001, there are two ways, like Z5 can be 1000 and Z4 can be 1, and Z5 can be and Z4 can be 1000.
Exactly right. So there will be two different ways, and you want Z5 to be P and Z4 to be, Z5 to be 1 and Z4 to be 1000, right? So it will just be 2PQ. PQ plus PQ. Let me just maybe write it. Okay, so what I mean to say is that this will just be the probability that you get Z5 as 1 and Z4 as 1000 plus the probability that you observe Z5 as 1000 and you observe Z4 as 1. So now the chance of this happening, so to observe Z5 as 1 is P. So this is going to happen with probability P. So remember, even though I have Z subscript T here, the numbers that this ZT takes and the probability with which it takes these values do not in any way depend on T. So this is just going to be P, and to take a value of 1000, it has a chance of Q happening. So again here 1000 first and then this next. So this is just 2PQ. Does this make sense to everyone?
Yes, ma'am.
Okay, so this was the first part. This was kind of, I guess, easy. Now let's see what's going to happen in the second part of the question. Okay, so we are, the same thing is asked, but again we are given that at X4 we have observed 1001. So how do you guys think this is going to change the probabilities?
It will be 0, right? Because it has to be either 1 or 1000. So again, x5 will, it will be similar, right? So probability x5 equal to probability z5 plus z4 equal to 1001.
Wait, what did you say? So you
They've
said
given the value of x4, not z4.
exactly right. And again, yeah. So it is x4. So this is not that xt is equals to xt minus 1 plus zt, which is the usual case that you have. Here, this is zt plus zt minus 1. So it's completely separate from xt.
Would it be the same because x5 is not dependent on x4?
Okay, and why do you think x5 is not dependent on x4? Have they given that to you in the question? We only know that zt's are independent, right? We don't know anything about xt being independent of each other.
I mean, the equation of xt, we can't see xt minus 1 anywhere, so I thought.
Yeah, I know. So, okay, let's just try to stick to our rules. So if I have probability of x5 being this, given that x4 is this, first of all, I should just use my Bayesian theorem to discard this conditional probability and write it in terms of something that I understand much better, right? So I will rewrite this thing as the probability that I observe my x5 as 1001 along with the fact that my x4 was also 1001. And this will be upon the probability that you observe your x4 as 1001. Right? Okay. So now what else do we know?
So x4 equals to 1001. The denominator can be written as 2pq, right?
Yeah, so this is precisely going to be the same as the previous case. So yeah, the denominator is 2pq. But what about the numerator? So let's just try to even write this x's in terms of z's, which we know much more about than the x's. So what I can write here is, instead of x5, I'm just going to write this as z5 plus z4, taking the value 1001, and here I will have z4 plus z3, taking the value 1001. So now, Vanshita, can you see that this value of x4 and x5 are not quite independent, right? Because the very value that you will have here for Z4 will influence the values that your Z5 can take here. So if you say that your Z4 here is 1, then you know that this Z5 has to be 1000 and that this Z3 has to be 1000 as well. And if you assume your Z4 to be 1000, then you know that this Z3 should be either 1, this should be 1, and this should also be 1 for this thing and this thing to hold true. Do you guys get that?
Yes.
Yeah, right. So that is what we'll have to do now. So again, how do I do that? So who would want to dictate what should I write next? So what did I do? I saw the common link between this and this, because again, when I have a comma, I'm saying that this should be true and this should be true simultaneously, right? So I know that this Z4 and this Z4 should always be the same. So using that information, I know that this Z can only take two values, right? So I will assign a particular value for this Z4. So what I can do is I can write that the probability that my Z4 takes a value of 1, then if I know that if my Z4 takes a value of 1, my Z5 and Z3 will have to take a value of 1000, right? And the another way this could happen is the probability that my Z4 is 1000 and my Z3 and Z5 is just 1. And this will be again everything upon 2pq. All right. And then what should we do next? Now we just have to figure out the probabilities of this. So Z4 is 1 with probability P. And here you will have Q square. And here we have Q times P square and all of these upon 2PQ. So many of you would think that this is the end of the answer, but again, if you can clearly see, you can kind of do something else. So if you take PQ common, you are left with P plus Q in the numerator upon 2PQ. And this and that will cancel, and you know that P plus Q is just 1. So 1 by 2 is the answer, final answer that you will get. Any doubts? Any doubts? Anyone? Okay, I'm taking that as a no. And you can stop me now if you have any doubt. Okay. So we can do the C part similarly, I guess. Okay, so this is kind of interesting. We have two things in the conditionality now. So again, I'm just going to use my Bayesian theorem here. So what I will write here is the probability that my x3, x4, and x5, all of them take a value of, so all of them take a value of 1001 upon the probability that, so it will only be these two, right? The probability that my x4 is 1001, comma, my x3 is 1001. Okay, so now how do you figure out this denominator? Anyone? How will you figure out this denominator here?
It will be the same, right? Half only will take.
Why do you think it will be half? What was half?
It will be PQ square plus Q P square.
Exactly, right? It will be the numerator that you got for this guy here.
Yeah.
So it was, I guess, PQ times P plus Q. So this is what I remember. Yeah, so I guess here, yeah. Okay, so this will be your denominator, and then in the numerator you will have to solve for this in the similar manner we did it with the other case. So here you will have something like, so you will start from Z2 because you have X3. So you will start from Z2 and Z3. And then for X4, you will have Z3 and Z4. And then for X5, you will have Z4 and Z5. So maybe we should start with the first common thing, that is Z3. So I know I can assign only two values to my Z3. So let us say so this is Z2, Z3, Z4, and Z5. So I'm trying to see what are all the possibilities based on if I assign Z3 my value 1 or 1000. Okay, so if I assign Z3 the value of 1, what will be my value of Z2? So I know everything should add up to 1001, right? Each of these should add up to 1001. So if my Z3 is 1, my Z2 should be 1000, right? And if my Z3 is 1, my Z4 should also be 1000. And if my Z4 is 1000, my Z5 should be 1. And let's say if I'm doing here, my Z3 is 1000. So now this is the another case that I'm considering. Then if my Z3 is 1000, what should be my Z2? 1. And this should be 1 as well. And this should be 1000. So these are the two possible scenarios that you will have. So I guess you have 2 1s and 2 thousands everywhere. So it's just going to be P square Q square plus P square Q square. Does this make sense? And you can basically do the PQ will cancel out and you'll be, so this will just become 2p square q square upon pq, p plus q, p, and you'll have 2pq, yeah, p plus q is just 1. So it's just going to be 2pq. That will be your answer, I guess. Any doubts in this? So again, I think, see, the only thing that you have to be very careful when you are dealing with these sums is you have to make sure that you have taken each and every possibility that is there into account.
Understood.
So again here, how did we ensure that we take into all of those possibilities? We try to find a common thing. So you could do the similar thing with Z4 as well. But if you start with Z5, I mean, you could still do the same thing because you could move and work backwards.
Yeah, understand.
So yeah, I guess. Yeah. Any doubt in this?
No, ma'am. Thank you.
And thank you very much, Sahil. Others? Any doubts?
No, ma'am.
No, ma'am.
Okay. Perfect. So I guess this was a good question. All right. So let us move to the 2.6. Now we want to figure out the stationary distribution. And how do we do that? Does anyone remember the statement of stationary distribution? What does it say? So Isha, you might not have covered stationary up until now, right?
Ma'am, I had covered the stationarity part. Like, is this the same thing?
No. This is a stationary distribution. So I guess you can, stand out for this question. And I guess for the rest of you guys, I'm asking you guys the question. How do we define what is the equation for stationary distribution? Or rather, if you guys can give me directly the equations, I'd be more than happy for this stationary distribution. I want to figure out it for this P guy here.
So the first equation will be 1 by 2 pi of phi equal to pi 1.
Okay, so you say the first equation will be 1 by 2. Okay, so again, I think you all do know what is stationary distribution. So the very easiest way to figure out the equations is one thing. You can just write this pi p equals to pi, right? This is my formula for the stationary distribution, is that if today I am at this particular state, and if I progress one time step forward, I am still where I am. I mean, the probabilities of being where I am still remain the same. So this pi p equal to pi is the equation that we have for stationary distribution. And here we have 5 states. So you can define pi as pi 1, pi 2, pi 3. Okay, let me not just do all of this stuff. I don't have to write it. I can go directly here. Yeah, so if you see, you can actually write it in these terms. And what you will have here is, so this is your vector pi, this is your transition matrix P, and this is your vector pi again. That is what you expect to get. So this pi 1, pi 2, and pi 5, you expect that these will be always the same. And then what you can easily do is you can just do the multiplications here and here. So you multiply this with this, and you will get this. So again, if you do this, what you will have is pi 1 times 0, pi 2 times 0, 0, 0, plus pi 5 times a half. So that will be your very first element in this vector pi. So that is why your half of pi 5 is equal to pi 1. And then you will multiply this with this. So you'll have pi 2 times 1/2 plus pi 4 times 4/5, and then pi 5 times 3/10, and that will be equal to your second element, which is pi 2, and so on and so forth. So you will get these equations, and then you know that one of these equations is going to be redundant, and then you will use the fact that all of these add up to 1 to figure out the actual answer of all of these pi's. So I'm not going to solve that. Instead, let me just, so I am assuming you guys don't have any doubts with solving of stationarity distribution. It's the most mechanical thing I can ever tell you guys to do. But I guess you guys should practice it at least once or twice. So these 2 questions I'm going to leave for now. And let us try to do, I guess, this question. What is this? Chain 1, define chain 2, and what is this? Draw a transition diagram, which is fine. And then you have to figure out these probabilities. Okay, let's do something where we have to figure out whether the chain is periodic or not, I guess. So I guess here they have defined 2 chains. For the classroom purposes, I'm going to stick to the first chain here, which seems to me a bit easier. I mean, just because of 4 states. So there's a nice, okay, half to go from everywhere and then from one, okay, I think. So if I were to draw the transition diagram for this thing, from 1, I'm going to transition to 2 and 4 and 3. So let me just try this. I think this might work. So 1 to 2, again, I'm not going to write any probabilities because all the probabilities are just half. So you can go from 1 to 2 and you can go from 1 to 4. From 2, you go to 1 and 3. From 3, you go to 4 and 2. And from 4, you go to 1 and 3. Yeah. And all of these have a chance 0.5 of happening. Okay. So now that I have already drawn the transition diagram for you guys, I want you guys to figure out these probabilities. Okay. Maybe I should. Yeah. So now we don't need any of that question, right? This is all the summary of the question. And again, these are all 0.5. So I guess we are fine with that. So let us try to do the part A first. Given that you have observed x0 as 1, so basically at time 0, you are in state 1. Okay, so maybe I guess to start off with, you guys can do this kind of a table. 0 time to, you're traveling till 1, right? So you go from 0 to 1 and then you go from 1 to 2. So in time 0, you are at state 1, and in time 2, you are at state 1. So what all are the possible values that you can take in time 1? So again, the very first thing that you should know is that wherever you are at time 1, you should be able to reach state 1 in one time step. So if you see, you can reach state 1 in one time step only from either 2 or from 4, right? So I guess the only 2 possibilities that you think you might have here are 2 and 4. But again, now you will also think, is there any chance that I go from 1 to 2 and then 1 to 1 and then 2 to 1? Yes, so 1 to 2 and 2 to 1. Great. 1 to 4 and 4 to 1? Yes, right? So I guess these are the these are the possible paths that you will have. And 1 and 2. So the transition, this is again going to be 0.5 squared and this is going to be 0.5 squared. So you add up and you get something, I guess, 0.5. Right? Does this make sense? So now I want you all to try by yourself. So this was the A part that I did, but now let's try to do the B part. How will you guys do the B part? So again, I have my own way of thinking about these probabilities. I try to write time and states, and then I try to see what are the possible values I can reach 1 and so on. But you can have your own method of thinking as well. So I guess Let's try to do the B part. So I want you all to try this by yourself. And tell me what method you used and what answer do you get by using that method. So again, we are given where we are in time 0 and we have to figure out what is the chance that you will still be at state 1 in time period 4. What is the best way to solve this? So I think if I try to list down all the possible paths here, it's going to take a whole lot of space and a whole lot of time, right? So what method have we studied to figure such things out?
Ma'am, I have solved it using, suppose if we write P, then 1, and it is for time 4. So we can multiply that, taking the initial as 1, 0.
Yeah. Right. So basically you will have to see the number of transitions you are making. So I guess if you start at 0, 1, 2, 3, and 4. So you move from 0 to 1, 1 to 2, 2 to 3, and 3 to 4. So you're making 4 different transitions. So you know you can reuse your transition matrix to 4 and have a look at its 1, 1 element. And that will give you the chance that you observe yourself at state 1 after 4 transitions. But again, that is not what we want. We are given a condition that at x0 you find yourself at 1. So let us define that as 1, 0, 0, 0. And then you will multiply p to it and you will move to 1. And then basically if you raise it to 4, if you do these multiplication and if you check its 1/1 element, you will get the answer. Does this make sense to everyone? So what you will have to do is basically 1, 0, 0, and then you will have this full transition matrix written here. So you will just have to take the first row of the transition matrix into account. So I guess it's going to be something like, so from 1, you cannot go to 1.
Ma'am,
From
this
1,
you're explaining for the second B part itself, or is it for the fourth one?
no, B part, this B.
Okay. Why can't it just be P raised to 411?
Okay, so P raised to 411 because we are given a condition, right? We don't only want to know what's gonna happen here. We want to know given that we are at 1 in x0. So given that we are starting at 1. So how do we know that we are starting at 1? I mean, if let's say x0, you are at 4, then the chance that you will observe yourself at 1 in fourth time period will be a bit different, right? Than if you are at state 1 in x0. And that is why you take into account this particular thing by writing the probability as 1 that you find yourself in state 1 and 0 for the other cases.
Okay, so just because we want only the first row of the matrix, we are doing it this way.
Yeah. And I mean, so it will just save you a whole lot of calculation, right? You won't have to figure out the whole of matrix every single time. So you will basically be multiplying these, but again, you will always just get the first row because you have a 1 here and you have 0 elsewhere. But this will only be the case for the very first multiplication, because once you do this, what you will get here is this thing times p, you will get, so from 1, you can only go to either 2 or 4, right? So you will have 0 here, a half here, a 0 here, and a half there. So this is what you will have now. And then you will again multiply this with p. So you will multiply p 4 times. So here you have 0, half. So here you aren't restricting yourself to just the first row. But again, you are restricting yourself to the first row of this p raised to 4 matrix, because every time you get only a one particular row here. So you are only looking at the first row. Basically, you only want to care about the chance that you will land up in state 1. So the first row will be about state 1. And again, that is why the very fact that you, okay, so maybe I should say that this one here is why you take this one. But this one is, okay, so it's not even this one. Basically, the very fact that you want to figure out this for a particular state is why you have only this one row vector. You would still get only one row if, let's say, this were 2 or 3 or 4 or anything else. Does this make sense?
Yes, ma'am.
Okay, so now let me erase all of these and we'll directly, okay, so I guess you will just have to multiply it 4 times and you'll see what the answer is. And I'm not going to do that. So you see, you will get 4 marks and you'll get 2 marks. This is like really good stuff, I would say. Okay, now you have to explain whether the chain is irreducible and or aperiodic. Okay, so we could clearly see that we can move from any state to any other state in any number of time steps. So it is irreducible. But is the chain aperiodic? What do you guys think? Is the chain aperiodic?
No, ma'am.
No, right? And again, the very fact that we have established that my chain is reducible will know that the periods of all the states are going to be the same, right? And there is no transition from a state to itself. So again, that kind of gives away that this is not aperiodic. So this is a periodic. So I think, I'm not going to draw the whole transition again. Wow. Okay. So yeah, if you want to figure out the periods of, let's say, any particular state here, let's say we do it for 1. If I am at 1, I can come back in how many steps? In 2 steps. Or in 1, 2, 3, 4. Or basically 2, 4, and so on and so forth, right? I mean, basically it will just be 2, 4, I would say. What do you think? Will it just be 2, 4? You can also go from 1 to 2 and then 2 to 3, back to 2 and then back to 1. So that will still be 4. But let's say we do 1, 2, 3, 4, 5, 6. I mean, you can just go on and on here. So you'll always be, you can increase it by 2 every time. Or you can go on and on in the loop here before you reach 1. So I guess the common factor is just 2. So the period of all of these states is going to be 2. I mean, we weren't supposed to figure that out, I guess. But yeah, still. All right. So I guess now that we have figured out, we can clearly see that the chain is reducible and the chain is not aperiodic, right? So the chain is periodic. Okay. Now, what is the 4th question? I guess this is a very interesting question. Yeah. So what do you guys think about the 4th question? Explain whether or not the process will converge to a stationary distribution, given that it is in state 1 at time 0. If it does converge, determine the stationary distribution. So they are saying to us that in time 0, you find yourself at state 1. So what do you think? Will this chain ever converge to a stationary distribution? And does there exist a stationary distribution? So we can maybe go back to all the rules. Yeah, I guess someone was trying to say something. Go on.
Yes, it will convert to stationary distribution.
And why do you think it will converge to a stationary
Because
distribution?
it is irreducible and also aperiodic. So according to like the property, if it is irreducible and aperiodic, it converges to stationary.
But we just concluded that this is not aperiodic, right? This is periodic. So the statement says that if we have a irreducible and aperiodic, okay, so aperiodic and aperiodic is right, I guess. This is a bit confusing when I say it. So irreducible and aperiodic converges, right? But here we do not have aperiodic. We have periodicity, right? It would be aperiodic if, let's say, there was something like this, right?
Sorry, I'm not confused.
You are confused, or do you understand?
It's clear now. I just got I
Okay.
got confused for a bit.
Yeah. I think it's all right. Yeah. So, okay. So we know that this will not converge to a stationary distribution, right? Because, I mean, this is not reducible and neither aperiodic. But again, we cannot just conclude that on the basis of that statement, because you might have some convergence even if you don't have aperiodicity. So, but again, I think what will help us is if you have a look at this here, where they have, drawn all the multiplications and done all the transitions. So if, let's say, you start at state 1 in time 0, this is what happens. So you expect to be in state 2 and state 4 half of the times. And then in the second time step, you expect to be in state 1 and 3 half of the times. And this thing continues, right? So you see that this process never really settles down if you start at 1. So you can clearly say that this process will never settle down. But, okay, what is this? Oh yeah, this is, wow. You guys should never do this. Do not sit and calculate all the paths. Yeah. So what does it say? It will not converge, right? It will not converge to its stationary distribution. But again, because the chain is irreducible and because we have finite number of states, we know that there is a unique distribution. So there is a unique stationary distribution, but it's just that you will never achieve it, at least if you are starting in state 1 in time 0. Does this make sense to you guys? Any doubts with this? I think this was a good question. I think the fourth one was good. Okay, so now let us try to do another question. Okay, we can try to do this 2.10 and 2.11. I guess 2.11 is also a good question, but let's try to do 2.10 first. Okay, who would want to read this question? Meher, would you like to read this question?
Yes, ma'am. An author is about to start writing a book that will contain 20 chapters. The author plans to write a new chapter each week. However, when he reviews his work at the end of each week, there is a probability of 0.25, which is independent of the current state of the book, that he will not be happy with the one of the chapters he has written. In this case, he will spend the following week rewriting the particular chapter instead of embarking on a new one. He may decide to rewrite any one chapter, including a new one he has just finished, or one that he has previously rewritten. Let xk denote the number of chapters that the author is happy with the end of week k, and define x0 is equal to 0.
Okay, so what other information do we have? First thing that we should note is that the author plans to write a new chapter each week. So this guy cannot write more than one chapter in 1 week. So we know that in 1 week, he can only write one chapter. And that chapter could be a new chapter or some chapter which he is not happy with that he has previously written. So he'll rewrite that chapter, right? So you know, if let's say I have passed 5 weeks up until now, there's no way he can write more than 5 chapters in 5 weeks. And the least possible number of chapters that he could write in 5 weeks is 1, where he just keeps rewriting the very first chapter he wrote in the first week if he's not happy with it, right? So I guess that's it. And then we are given the probability that he will be happy. So 0.25 is the chance that he will not be happy with one of the chapters. Okay, so it says with one of the chapters, right? So it doesn't necessarily mean that, let's say, if you are in week 5, you can only rewrite chapter 4. You can rewrite any of the chapters that you have previously written. It could be chapter 1, chapter 2, or any of the chapters. So I guess we have that. And then what do we have? I guess that is all the information. Okay, so here it's kind of happy. I mean, it makes me happy that we are given what my state space would be, right? So the very first question asks me, explain why xk can be modeled as a Markov chain. And they have given me in the question what my xk is. So what is my xk? It is the number of chapters that the author is happy with at the end of week K. So you know that at the end of week 0, there are no chapters. So of course, this x0's value is going to be 0. All right. So again, they're asking us why can xk be modeled as a Markov chain? So again, I think the very first thing that you will have to prove here is that xk has Markov property, right? And how will you do that? Anyone? What explanation can you give to explain why this xk can be modeled as a Markov chain? Take your time.
So, ma'am, we are told that he reviews his work at the end of each week and not just the chapter that he's written in that particular week. So, we can say that, like, even after he's done with the second week, he's gonna review all of his work, right? So,
Yeah.
so like xk plus 1 depends on xk.
Okay, so you're saying xk plus 1 depends on xk. Yes.
So
But you also have to kind of prove that xk plus 1 does not depend on xk minus 1, right?
Okay.
So you'll have to prove that xk plus 1 depends only on xk.
Can we say that xk, like xk minus 1, xk will be inclusive of xk minus 1?
Yeah, that is true. That is true. But again, I mean, so okay, you will have to. Okay, I think Isha, you get the idea, and I think you have understood why this can be modeled as a Markov chain. But this is not what a examiner will be happy with, because you will have to precisely write this in words. So whenever you are saying that xk can be modeled as a Markov chain, the very first thing that I would do is not talk about xk plus 1, but talk only about xk. So what I will show is that xk depends only on xk minus 1. But again, this is not going to make examiner, cut your marks, because I mean k plus 1 is just another placeholder for k. So you can still do the same thing for xk plus 1 and xk. So let's just do it for this for now, I guess. So what we have is xk plus 1 and xk. So xk plus 1 is the number of chapters that the author is happy with at the end of week k plus 1. So I know that the number of chapters that this author is happy with could either be equal to the chapters that he was happy with at the end of xk, at the end of week k, right? And when would that be the case? So when will my xk plus 1 be equal to xk? Maybe, before we do all of that stuff, let's just write in simple numbers. So we can have 0, 1, 2, 3, and so on and so forth, right? And the maximum that you can have is 20 chapters. So let us say these are the chapters that my author is happy with. Okay, so now if I'm at time 0 and I am at 0 state, what is the chance that I will move to 1 in the next state? Sorry, in the next time period. Anyone? What is the chance that I will move to 1 in the first week?
0.75.
Exactly right. It is the time where I basically write one chapter and I'm happy with it. Okay, and now let's say if you're at 1, what is the chance that you will go to 2?
Again 0.75. Also,
Right.
can we say that it is Markov also because all of the probabilities are independent and the same?
Okay, and the same does not matter, but the fact that they are independent matters. Their same has nothing to do with it being Markov.
Okay.
Yeah, but now let's say if I give you 1 to 1, what is the chance of 1 to 1?
0.25.
Right? 1 to 1 is just going to be 0.25.
Yeah,
because
he cannot go all the way back. He'll just review the state
one
at
chapter.
that point of time. Yeah.
Yeah, and again, he can only review and rewrite one chapter within a week. So let's say if he's happy with one chapters, but now in this particular week he's not happy with the chapter that he has written, so he will rewrite that chapter itself again. So he'll only have one chapter at the end of the second week as well, and the probability that he'll not be happy and he'll rewrite is 0.25. Okay, so you see that my xk plus 1 can either be equal to xk. So my 1 can either be equal to 1 or my 1 can move to 2. So my xk plus 1 can also be xk, x subscript k plus 1 can also be xk plus 1. And the probability that these will be equal is 0.25, and the probability that these will be equal is 0.75, right? But again, so you can say that the distribution, the probabilities and the values that this xk plus 1 will take depend only on the value of xk, right? So once you know xk, you can easily determine xk plus 1. You do not need xk minus 1 and the previous information about the chain, right? So that is one thing, and that is why you can model this thing as a Markov chain. And whenever you do that, you should always also write the state space, the sample space of the state space. So you can say that your xt is actually going to follow a discrete state space. So it is going to be 0, 1, 2. And again, you know that the maximum it can have is only up until 20, right? So that is what you will have. Any doubts in this?
Ma'am, can you explain this once again? Why it is Markov?
Why it is Markov? Okay. So when I write my distribution of xk plus 1,
Means in
the
the
values,
statement where he has written, including a new one he has just finished, or the one that he has previously rewritten. Means it doesn't mean that he can rewrite any number of previously written books. Like
no.
not the,
So here the author plans to write a new chapter each week, right? So an author can write only one chapter in a week. So if let's say he's not happy with the chapters up until now, he can choose any one of those chapters and rewrite that chapter again this week.
Okay, got it.
Got it? So that is why, and again, xk can only take values from 0 to 20 because this is the maximum number of chapters that you can have. Anything else?
No, ma'am.
All right. Okay, so this was about part 1. Okay. Let me just, will we need any of this stuff? I guess we might need. Okay, I'm just gonna clear everything for now. Let's see. Okay, so let us try to figure the second part out. What does it say? It says us to figure out the probability that the author will complete the book in exactly 25 weeks. Okay, this is a good question. So we want to figure out the probability that the author will complete the book, right? So when you say complete the book, you know that my x20 is what? What should be the value of my x20 here? Oops, no, not x20. We are looking at 25 weeks and 20 chapters. So the author should be happy with all the 20 chapters by the end of week 25th, right? So this is what we know. Okay. So what is the probability that this will happen? Anyone? What comes to your mind?
0.75 raised to 20, and that is the number of chapters he's happy with. And he took 25 weeks. So for 5 weeks, he wasn't happy. So 0.25 raised to 5.
Does everyone agree with this? So this is partially correct, I would say. But again, these 5 chapters that he's not happy with could be any chapters, right? And this could happen in any of the weeks. So there will be different sample paths, and you will have to account for the number of ways you could have chosen 5 chapters which you will rewrite out of how many chapters. So again, this is a bit weird because you will have 19 here instead of 20. Sorry, you won't have 19. What you will have is actually, oops. So here, what you care about, you will have is 24, not 25. Okay, so let me explain that. So ideally, if we are supposed to choose these 5 chapters that the author has to rewrite from the number of chapters that he is writing in 25 weeks, you would think that this should be 25 C5, right? Because if let's say you have 4 spaces, you can choose one space in any of the 4. So you get 4C1, right? And if you care about 2, you will have 4C2. So here we are talking about 5 different things and we have 25 blank spaces. But you also have to take into consideration that the author should always be happy with his last chapter, right? He cannot be unhappy with his last chapter. So there's no way he could be unhappy with whatever work he has done in the last week, right? So you will have to forego that part, and that is why you subtract 1 from the 25 weeks that you have, because he'll have to be happy with the chapter that he writes at the end. So this is the kind of again, I think if you have do you guys get what I'm trying to say?
Ma'am, I think instead of last chapter, it will be better if we say the final review. Like when he review the entire book, the final, the 25th time, then he will be happy. So
Yeah,
24 times he wasn't
sense.
happy, and then the 25th time he was.
Yeah. So 24 are the total number of times, out of which 5 times he was not happy. And for the last one, he has to be happy, right? Do the rest of you understand this?
Yes, ma'am.
Yes, ma'am.
Vanshita, are you there?
Yes, ma'am.
Do you understand this?
Actually, it's kind of getting heavy right now.
Okay. All right. So this is the last.
Yeah,
Okay,
no, but
let's.
I'll go through it once again,
Yeah.
like my mind is finished.
I think you'll get it. I think you'll get it. We are going to wind up here. I'll just explain 2.11 in 2 minutes. Don't worry about that, I guess. Okay. So this will be your chance that you will complete the book in exactly 25 weeks. Not more, not less. Okay. And I guess for the third part, what is it? Calculate the expected number of weeks it will take the author to this is really good question. Okay, so what do you guys think you should do for the third part? So to calculate the expected number of weeks, we will actually be okay, let us just try to do this now. So there is something that we'll be doing, but it's not quite exactly similar to the holding time or the waiting time that we're doing in the lectures. But I guess, yeah, we should still do this. So we want to figure out the expected number of weeks it will take the author to complete the book. Okay, so what is the minimum number of weeks that the author might take to complete the book? Anyone? The minimum number of weeks.
20.
20, right? So we know that the minimum number of weeks that the author will take to complete the book is 20. And let us say that number of weeks I denote by n. So the probability that my n will be 20 is what? And this will happen when he is always happy with all of the chapters that he has written, right? So the probability of this happening will be what? Anyone?
0.75 raised to 20.
Exactly, right? So every time you write a chapter, he's happy with it. All right. Then I know that if he's unhappy with one of the chapters, then you will have n as 21. And what will be the chance of that happening? It will be something similar to this, right? So I'm saying that he finishes the book in exactly 21 weeks. So that will be, so I know that the very fact that he has finished the book, he is happy 20 times. And because there's one added extra, so I know he didn't really like his chapter once. So I'll have this thing multiplied by 0.25. And again, this one chapter that he's not happy with, this could be in any of the weeks, right? Week 1, week 2, week 3. I mean, at least in week 1, there's nothing to be unhappy about. But in week 2, week 3, and so on and so forth, there will be cases where he could be unhappy. And again, there is only one case where he's unhappy. So there is only one case where he is unhappy. And there are 20 possible places where 20 possible weeks where he could be unhappy with his chapters. So I guess this will be your probability that you observe n is 21. So again, I think, so I'm using this method. Why? Because the another method that is shown in the book where they are solving this, I guess, is, so we haven't quite studied this yet. But again, if you try to read this, I guess you will still understand. But what I was trying to do, I guess, is something like this. So let me just erase everything. And this is what we have. So if you see it for 20, it's this. If you see it for 21, it's this. If you see it for 22, you get something like this. But again, I mean, this was actually a very sneaky thing to do. So you had 20 C1, and because of the Pascal triangle, you know that the values are always equal, right? So NCR is also equal to NC n minus R. And that is why 20C1 can also be rewritten as 20C19 and the value will be same. So I think let me just write the result here. So if you have NCR, this is equivalent to NCN minus R. And this makes intuitive sense, right? So what this result says is, let us say I have these 3 blank spaces. And if I'm trying to write this 1, okay, let's say I have this 3 numbers, 1, 2, 3, and I have to check out all the different possible ways I can write this 1 in here. So I know I can write my 1 here, or my 1 here, or my 1 here. But the actual number that I will have will also differ on the basis of how I write this 2 and 3. So if I rearrange this 1, or if I rearrange this 2 or 3, it doesn't matter, right? The number of ways I can do that will always be same. So that is why NC1 is going to be same as NCN minus 1. So here N is 3. So my 3C1 is going to be same as 3C2. Does this make sense? Does this make sense to you guys? Are you guys there?
Yes, ma'am.
Okay. Okay. So, I mean, that is basically the reasoning behind this particular result. And using this, you rewrite these probabilities, and then you just basically have to use the fact that this looks a bit like negative binomial distribution. And so again, I see that this is not the first thing that will come to your mind when you see this question, until and unless you have seen this kind of a question before. So you will do this method. And I guess this method is fine, and we'll be doing this method soon. But again, I think if you read through it, this is very much easier to understand as well. But I'm going to stick to this method for this. And again, you clearly see here the pattern, and you see that this kind of has type of negative binomial distribution, where your K is 20 and your P is 0.75. So you just take its expectation and you get the number of weeks, the number of expected weeks that you will have. I think for people who do want to know how to solve this using this method, you can actually, so let me just try to explain. So what I'm going to do here now is, we assume that my MK is the expected time until the book is finished, and this K is the number of chapters that you have completed so far. So again, this is just something very nice. And what I'm going to do is, I know that my K is the number of chapters that I have completed up until now. So what all are the values that my K can take? So again, my K can take values ideally from 0, 1, and so on and so forth till 20, right? So my K can go on up until 20. Okay, and now what they are trying to say is that, so here they are only considering K from 0 to 19, because let's say if you are satisfied with all the chapters, then there's nothing to look forward to. So here they're trying to define a particular equation of what's going to happen when so this is basically the time that you expect for the book to be finished. So let us say if you're looking at M20, then the book is already finished, right? So there is nothing that you will wait for after it. So MK will just be basically, it will be the time that you have observed up until now. So I guess that's fine. So now you understand why they have written K going from 0 till only 19 here. Any doubt so far? Any doubts? I'm taking that as a no. So forget about this equation. Let us say if I tell you that I care about the expected time until the book is finished, given that currently I have written 18 chapters. Okay, so if my number of chapters completed are 18, how much time do you think I need to finish the book? What do you guys think? What do you guys think this M18 will be? Anyone? It's very difficult to think, right? Because if I have M18, which is the expected time, and I mean, I'm looking at the expected time, right? This is not just the time that I will take to finish the book. If I finished 18 chapters, this is the expected time. So it's really difficult to easily figure out this from first principles. And that is the reason you use M18, you use M18 or let's say M17 to derive M19 and so on and so forth. So here you are writing a equation. But again, let me just maybe write this equation again here. So if I'm looking at K18, then what I will have? I'll have 0.75 M19 plus 0.25 M18. So if you were to interpret this particular equation, what will you say? So the expected number of time that the expected time that you expect, the expected time until you expect the book to complete, given that you have finished 18 chapters, what will it be? So they're saying that it is just going to be 1 plus 0.75 M19. Okay, so we see what is M19. Anyone? Can you explain me in words what is M19 here? Okay, maybe we can just use this. So M19 is the expected time until the book is finished, given that there are currently 19 chapters completed, right? So if you have finished 19 chapters already, then what is the expected time that you will finish the book? So now if you're looking at M18 and you want to see that the relation there is between M18, M19 and again, so basically how can you reach 18? So I think the very easiest thing is to just do this thing, right? So on and so forth, and here you will have 18, here you will have 17, and here you can have 19, right? So the various ways you can reach 17 to 18, 18 to 19, and then you can go back from 19 to 18 as well, right? Sorry, you can have this thing, you can't go back from 19 to 18. So this was the kind of chain that we were looking at. Let's say if you've completed 17 chapters up until now, there's a possibility that in the next week you will complete one more chapter, right? And you will have 18 chapters completed. But again, there is again a possibility that if you have completed the 18 chapters, then you will still be unhappy with any one of the chapters that you've written before, and you will find yourself at 18 again. And there's a possibility that you will find yourself at 19 again. Because let's say if you're satisfied, then you can move from 18 to 19 as well. But again, here, what we have is M18. So the expected time, and I mean, here you are assuming that you have already finished 18 chapters and you have completed 18 chapters. So you are here right now. So you have completed 18 chapters. And now you see what all can happen. So you can either stay at 18 or you can go at 19, right? And once you are at 19, what will you have? You can multiply this, the chance that you will move to 19 with the expected time that you expect your book to finish if you are at 19, right? So what you're doing is you're kind of using a recursion formula to do away with some calculations that you might have to do otherwise. So if you are at any state here, you see the probability that you will move to another state, and you multiply that with the time that you expect you will finish the book once you are at this state. So you're in a way bifurcating all the possibilities that you can have from 18, and you see how do you reach the other states and what is the chance of reaching that state, and then you just multiply it by the expected time for those particular states. Does this make some sense? I can see the class is silent. Did you guys understand what I was trying to say? I guess maybe not. Are you guys there? Hello?
Yes, ma'am.
Yeah. So I guess, see, I think the only issue with this method is that you cannot really come up with this equation if you don't have this in front of you. So I would never suggest to use this method because this is very, very tricky. So what I would suggest is forget about this method, and what you can do is just use this method. And now that you have already seen a sum like this, you know what to do if you see another sum which asks you to figure something similar, right? And we'll see how do we kind of use this method in our next lecture actually. So in next lecture, we are going to discuss this method. And I guess that will be much more complete view. And then if you come back to this question, you will see why do you get this particular equation here, I guess. So let me just say that this is it for the day, I guess. So the only interesting thing I find in question 2.11 is this part here. So I want you all to solve this question, and I think this is a very interesting question. So let's just not solve it in the class, and if anyone has any doubt, you can ask me, but do solve this question, I would say. And that's all from my side for today. And I think it has become a bit heavier, so good night, everyone. And I think we'll take another lecture. Are you guys, so will you guys be happy if I take a lecture tomorrow? Or do you guys want some break? So then I'll take lecture on Thursday.
Ma'am, any lectures are fine, but just like 2 hours is okay in a day.
Yeah. Okay. Yeah, all right. All right. Okay, so I guess tomorrow we'll have another lecture where we can discuss questions from chapter number 3. So it would just be, no, so let's have a lecture tomorrow, a proper lecture. And then day after tomorrow, I can discuss chapter number 3.